No electrical training is complete unless you know this basic formula, which is E stands for voltage, I stands for current, and R for resistance. A good trick to remember the formula is to say that this one, E stands for Edward, and R for Rebecca, and I for Irma. And the trick is simply Edward is the boss, and when the girls are working by themselves, the girls are, well, you know, hanging by their hands. But if a girl stays by herself and she goes over to see Edward, since he's the boss, she will be on top of her. So it will be here will be E divided by R. If it would have been the other case, the R would stay on the other side. Then Edward would have been the boss. He stays on top, and at the bottom will be Irma. This quick trick, it works really well. Anytime the girls are by themselves, they are hanging out together. But if the girl is with the guy, if the guy is with the guy will be on top of the girl because he's the boss. Another formula that I use a lot is the power formula, and power is equal to E times I. And one way to remember this is that current is what kills you, okay? So that definitely is harmful. And then voltage, you feel it. So current kills you, and voltage you feel. And so all you have to do is remember that you multiply the two that affect you, either the one that kills you, the one that feeds you. Or resistance, okay, this over here has a resistance. However, if I were to put a multimeter, it will say that it's OL. I'm touching the resistance of it, but I'm not getting killed. I'm not feeling it. So therefore, resistance is what you don't feel, and you do not use that for your power equation. All right, so now let's talk about how to use this stuff. To use it, okay, and here they got us a power source that they're giving us 15 volts. And they're saying that when the switch is closed, the light comes on, and that the light consumes 5 amps. So what will be the resistance? The formula was E equals I times R. They just gave us the voltage, which is 15 volts. They gave us the current, which is 5 amps. And this is the symbol of ohms. This is in ohms. And this one is in amps. So what are we missing? R. So at that point on, we clear for R, and R stays by itself, and then E goes on top, and I goes on the bottom like we studied earlier. All we gotta do is plug in the numbers. We use 15 on the top, 5 on the bottom. I'm gonna circle this to kind of forget about it. And if I do that division, at the end, R is going to be equal to 3 ohms. And now how we use the formulas, okay, we got in here a simple circuit, okay, we got a battery that has 15 volts, okay, we got a switch, and whenever the switch is closed, it turns on the light, and it consumes the light is consuming 5 amps. So what's the resistance of the light? So at this point on, we're just going to go to our formula. E is equal to I times R, like we discussed earlier. And we're just going to find the numbers that we know. We know 15 volts. The E is voltage. So that's 15 volts equals I, which is current. So that's going to be 5 amps times R, which is what we don't know. We're going to clear our formula, and R is going to stay by itself, and then E, remember that we said that E will always go on top, okay? Or what I said, the analogy that he's the boss, that was Edward, and then so therefore if Irma is going to go on the bottom, it's going to go with him. She's going to go on the bottom, which is current. Now, at this point on, we just got to replace the numbers. Voltage is 15 volts, and current, we say, is 5 amps. So when we divide that, 15 by 5, resistance is equal to 3 ohms. And that's the symbol for ohms. And this second exercise, now we just want to know, by the way, this is a new source, this is an AC source, we'll talk about that later, but the switch is closed, the light is on, the resistance of the light is 5 ohms, and 2 amps is going through the circuit, so therefore what is the voltage, okay? And in this case, so back again, we go back to our standard formula, and we just plug in the numbers, in this case 2 amps on the bottom, times 5 ohms, and if I multiply this two, I'm gonna get 10 volts, and that is what goes over here. So that's the basics of how we use these formulas. Now we're gonna go a little bit more in depth, but for that we gotta talk about series and parallel circuits. That's pretty much what the new system is, or the new we need to talk about. And series we're gonna talk about here. And in series, what we say is that electrons, okay, whenever we leave the circuit, they gotta go through the same path. So we gotta go through resistor 1, resistor 2, and resistor 3. So as those electrons are passing, the same electron that left over here has to go through this point, that point, that point. So we, and this point on, we will say that resistor 1 is in series with resistor 2, which is in series with resistor 3. On the other side, now the electron can go either this way, so that electron will go that way, a second electron will go this way, so they are actually splitting. So that at this point on, even though they split, eventually they will join, and even though they left together, they split, and at the end they join themselves. So this section over here, we will say that these are in parallel. Resistor 1 in this case is in parallel with resistor number 2. And just if you were wondering, this is what I was saying, parallel. Now if you're wondering what is it that I was saying parallel for this circuit, and series, this is an I for this circuit. Now let's calculate these things. So this is a quick review, so I'm not going to spend too much time on this. For parallel, okay, what resistance is additive. So to add these two in parallel, we just simply use this formula, where pretty much what it is the total resistance, okay, is actually 1 divided by total resistance equals the resistance, or rather 1 divided by resistance 1, which in this case would be 5, plus 1 divided by the resistance number 2. Now in our case, our formula ends over here, but if we have more resistors, and so pretty much we will be replacing, if we have 5 branches, we will have resistance 1, resistance 2, resistance 3, 4, 5, and 6, all the way up to 5, because it will be 5 resistors. But in this case, we just end there. And now I'm gonna make a quick stop, because in this particular scenario, that resistor is the same as this resistor. So instead of using this complicated formula, what I'm gonna do is I just simply gonna forget about it, and since this value is the same as this value, and this is a parallel, and this is only true for parallel circuits that have all the same value, I can count resistor 1, resistor 2, so I got 2 resistors, so I'm gonna divide the same value. What's the same value? This value is the same as this value, so here is the same value of 1 resistor divided by the number of resistors. In this case, the number of resistors is 2 of them, which are in parallel, so I'm gonna put 2. 5 divided by 2, 5 ohms, so 1 resistor divided by the number of the resistors, which is 2, is gonna give me 2.5 ohms. 2.5 ohms is the resistance of these 2 resistors combined. Now here on the right, we got what is called series. In series, everything is additive. So what we're gonna do is, the formula is really simple. Total resistance is equal at resistance 1 plus resistance 2 plus resistor 3, and so on and so forth. In this case, we got 3 resistors, so that's what I'm gonna add. So 5 plus 5 plus 5. Now, in this case, the answer will be 15 ohms. But this would have been, the reason why I'm doing this is not because they are the same resistors. If this would have been 8, that would have been fine. I could have just simply put 8 over there. 5 plus 8 would have been 13, and plus 5 would have been 18. So for serial resistors, the values of the resistors do not, I repeat, do not have to be the same to use the very fast and only formula for series circuits. For parallel circuits, you got to get fancy, but if you got the same resistance, then you can just simply count the number and just divide by that number the same number. Let me explain with another formula, with another example. All right, and here's my other example. So I got multiple resistors 1, 2, 3, 4, 5, 6, and 7 in what is called parallel, and I'm just gonna add all those resistors to find out what is the equivalent resistance of the single resistor for this. All right, so I'm gonna start over here, and I'll show you why in a moment. If I just single these guys out, I'm just gonna circle them on here in red for better focus. I want to find out the equivalent resistance of those three. Well, the three of them are three numbers the same, 27, 27, 27. So I'm just gonna write 27. Because remember, this only works for the easy formula, but you should find this more often than what you think. Divided by 1, 2, 3. That's what they are. 27 divided by 3, it gives me 9. So the total resistance of this is replaced by 9 ohms. So I could say that those three resistors in parallel are the same thing as a resistor of 9 ohms. Now, I just go ahead and expand my selection, and I'm gonna grab all of this. So we got a 9 ohms over here, 9 ohms over here, and 9 ohms over here. So that's 9, 9, and 9. That's 9 divided by 1, 2, and 3, which gives me a total of 9 ohms. So what I am saying is that all of these, it gets replaced by a 9 ohm resistor. I take that back. I made a mistake over here. Not 9 ohms. 9 divided by 3 is 3. So all of this in here, it gets replaced by a 3 ohm resistor. Now, finally, if this is a 3 ohm resistor, and that is a 3 ohm resistor, and that is a 3 ohm resistor, that means that I can just simply divide 3, because it's the same number, 3 and 3, and just a newfound 3, and divided by 1, 2, and 3 resistors. So that is equal to 1 ohm. So all of this silliness, it was just to prove to you how simple it is just to use the quick cheat to multiply or to find the total resistance of parallel circuits. Finally, this is what they call a series parallel circuit. To solve a series and parallel circuit, in this case, you would for these ones over here, these three over here, they are in series, because an electron leaving this point, it travels and it comes back to these points. So these three resistors, you will use the very basic formula: total resistance of that sub branch is equal to resistance 1 plus resistance 2 plus resistance 3. Now, then once you find that sub branch, that will be in parallel with this resistor over here. We're going to call that resistor 4. So for that one, you will have this one, resistor 5, resistor 4, and resistor of this sub-branch in parallel. So for those, remember, and you will use, if they are the same numbers, and then you simply do what we just finished doing a moment ago. But if they are not the same numbers, and then you will have to go out there, 1 divided by the new, the resistance of the new circuit is equal to resistor 3. Oh, I take that back, it's to the bottom. Do not make that mistake. Resistor 3 plus 1 divided by resistor 4 plus 1 divided by RT of this area over here. So the number that we get over here, we'll put it over there. We will plug in that into our calculator, and that will give us the resistance, the equivalence of all of these. That would be, we could just erase all of that, and whatever that number that we get at the end of this equation, we will be put into an equivalent resistors in there. And finally, we could just simply back and use the same formula, resistor 1, resistor 2, and resistor 3 added, because, and this will be a series. Before, when we have all these branches, that was a parallel section. And then at the end, earlier, we had a series at the end, series at the beginning, and parallel in between. Now, let's make a little stop and let's talk about current, okay? So back on that formula, I equals I times R, okay? We didn't spend that much time talking about R, okay? We talk about resistance. So I, or the current, in parallel circuits, and by the way, this is back again P for parallel, or I'm just gonna write it, and the series, in here, well, in series is the one that most people like. Current is common. Since it's the same electrode that is traveling through all through the circuits, that means that if in here I measure 5 amps, later on, or rather instantly, that because light or electrons are traveling at light speed, if I read 5 amps over here, that means I'm gonna read 5 amps in that area. So that is when it says that a voltage, or rather current, is constant in a parallel circuit. So that means that if I read over here, I'm also going to read 5 amps. That means that in here I have 5 amps leaving. So it's the same 5 amps that I'm reading all throughout the circuit, because in series, current is common. Now in parallel, what is common is the voltage, which means if in here I got 15 volts, this light over here, and by the way, the circle with the 4 dots in the outside, or the 4 lines, that is a symbol for a light, and this is saying that the light is on because here the switch is closed. So where I'm saying that this light is consuming 1 amp, light number 2 is consuming 2 amps, and light number 3 is consuming only 1 amp, because they are different kind of lights, you could say. Now, what is the total resistance that is being provided by the source? The source is providing 1 amp for this branch, plus 2 amps for this branch, plus 1 amp for this branch. Now, what it means is that the source is providing 1 amp for branch number 1, 2 amps for branch number 2, and 1 amp for the third branch. So total, it is providing 4 amps, so that it can be distributed. Current is not common, not. What is common is voltage. Now, voltage is common because if I were to put my multimeter between these 2 points, I will get 15 volts. If I were to put them in here, I will also get 15 volts. The same thing as I will be here, I will be getting 15 volts. If I put my multimeter back in the series side, even if it's a 15 volt power source, and if I put it over here, I wouldn't be getting 15 volts. It's going to be, if I was to get 5 volts over here, it had to be somewhere with less than 10 volts, because at the end, the sum of the voltage drop on this resistor, that resistor, and these resistors have to be equal to 15 volts. Let me explain more about that. To better explain it, I have drawn this other circuit, okay, where I have a power supply right in the center, and that power supply provides us with 18 volts. Now, if I grab my multimeter and if I put it over here, I will be getting a potential of 18 volts. So if I want to know what the current is going through this branch, well, I just simply go to my simply useful formula, I times resistance. But since I want to find out resistance, I got it clear for I, so I'm going to do this over here. And I'm going to use it as my reference for everything, where E is going to go on top and R is going to go on the bottom. All right, so now that I have my formula, let's do some calculations. So I did say that since this is connected straight into the circuit, because if I just imagine that this wasn't, nothing else was over there, and if I was looking at that, then I could clearly see that the power supply is hooked directly across of that resistor. Also, it is hooked directly across the resistor all the way at the left. So if I got 18 volts from this point to this point, so that means 18 volts will go on top according to this formula that I'm using here, and 6 will go at the bottom. So 18 divided by 6, it will give me a current of 3 amps. But if I were to look from this point, looking at down here and looking up here, I'm gonna say that I also got 18 volts across this resistor. Now I'll back again 18 volts, and I got a resistor of 3 ohms. So 18 divided by 3, it will give me a current of 6 amps in this side. So voltage this to this side of the circuit is common, but the current is different. Now to the right side of the circuit, okay, here they're telling us that it has at this point 2 amps. That means that it was the same 2 amps that was a few microseconds over here, which it was the same as a few microseconds over here. Because remember I said that electricity is traveling at light speed. So as soon as instantaneously you see 2 amps over here, that means that you're seeing 2 amps all across of the circuit. So if I go back to this formula over here, well, actually back to my original formula, now what I want to know is what's the voltage drop on here. So if I know that this is a 2 ohm resistor, and I'm using this finger to point where the value goes, and 2 amp is going through that resistor, so that's what's going to go here. So 2 times whatever the resistance is, which is 2, is going to give me a voltage drop. So if I were to put a multimeter between this point and that point, the multimeter will give me a voltage drop of what is it? 4 volts, because 2 ohms multiplied by current at 2 amps will give me 4 amps. Now for this resistor over here, so you know what, for easier, I'm just going to use I times R, which I just copied this formula, put it over here. In this case, I got 2 ohms, and I got a current that I say that if at this point I'm getting 2 ohms, that means that 2 ohms was over here, so 2 ohms is, 2 amps, that's what I meant to say. So I got a 2 ohm resistor, and I got 2 amps going through the branch, so that means that the total voltage drop over there is 2 times 2, which is equal to 4 volts, and I got 4 volts over here. So far I got 4 and 4, I got 8 volts over there. This resistor over here has a voltage drop of, well, let's find out. The resistance is 1, the current is also 2 amps, so 1 times 2, that means it's a voltage drop of 2 volts across these 2 points. If I were to read the multimeter, and finally between this point and that point, I got 3 ohms, so I'm going to put it right underneath of the R's. 3 ohms times the constant value, which is 2 amps that is going through it, it will give me 6 volts. Now in this side, to the right side, what is common is amps. To the left side, what is common is my voltage. I had 18 volts here, 18 volts here, but my currents were different. I had 6 amps and 3 amps. That was on my parallel side. On my series side of the house, My current is constant, but my voltages were different. As a matter of fact, if I add 4 volts plus 4 volts, that is equal to 8 volts. And if to that, so this is over here, to that I add another 2 volts, which is this value. And then I take and I add this value over here, which is 6 volts. So 4 plus 4 is 8, plus 2, 10, plus 6, a total of 16 volts, which is less than this. I made a mathematical error somewhere, because the total voltages over here have to be equal to 18 volts, but it's not the case. And the problem and the error that I did is that earlier when I was preparing the formula, instead of making a 3 amp resistor, a 4 amp resistor, I made a 3 amp. So if I fix it by putting a 4 amp resistor, now I can just simply rework this equation over here, which is 4 times 8, 4 times 2 is 8 volts. So now I got 8 volts over here, which that eventually is what I put over here. So now let's do the addition again. 4 plus 4 is 8, plus 2 is 10, plus 8, 18. 18 is the same thing as 18. So now it does balance out. Now it makes sense. From this point to this point, see, all of this equivalent resistance, whatever that is equal to, it has a potential of 18 volts. This has 18 volts, does have 18 volts, and that makes sense. If you wanted to know what is the total resistance in this side, remember, all you had to do is add 2 ohms plus 2 ohms plus 1 ohm, which that would be 5 over there, plus 4, that will make it 9 amps of total resistance. 9 ohms of total resistance. If you grab this formula, if you pretty much deleted all of these and you replace all of this with an equivalent resistor of 9 ohms, then you could just simply do, okay, if I'm getting 18 volts between this point and this point, and I got 9 ohms at the bottom, my current will be 2 amps, which is exactly the same value that I gave you before. So it still checks out.